Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, which is actually a lab video, we're going to be looking at another post-quiz review, and this is for the Building a Spring Scale quiz. So let's pull up that quiz and I'm going to go through the questions that were on it and basically walk you through the answers. So let's continue with this quiz here. So the first question was, you made a graph for this lab. What were on the two axes of this graph? Okay, so let's open up our directions and take a look at what it is we're supposed to be doing, because that will help us when answering this question. So in the experimental instructions, it basically says get the spring, hang it, attach a water bottle or some other mass holder to the bottom of the spring, empty, then start adding some water or other masses to the bottom of the spring until the spring starts to stretch. Once that happens, write down the value of the amount of weight that you had to add before the spring would start stretching. Then add water in even increments of about 50 grams each from there. And then ultimately you make a table with the total weight added, the stretching weight, which is the difference between the total weight and this W0 value, and then also how much this thing stretches by. So then it says, along with this table, you should make a graph with WS, the stretching weight on the y-axis, and X, the amount the spring stretches, on the x-axis. So this is telling me that we need to put weight and stretch on the two axes of the graph. So we're basically making a graph of weight versus stretch. So looking down here, there's an option for weight and stretch. We select that. Then it says, what did you use to make a scale in this lab? The scale itself, to clarify, is the thing that you're actually using to measure the weight with. It's the thing that's actually changing as you add more weight to it. So that would be a spring. And then question number 3, suppose you have two scales, both of which operate using the stretching of a spring. Both springs have the same initial length and both have the same maximum length. But scale A measures up to 50 pounds and scale B weighs up to 100 pounds. Which scale likely has the greater spring constant? So you may have to pull up your directions to try and understand what the spring constant is. Basically, you look down in here and it says once you have a line for stretch versus stretching weight, then find the slope, and the slope is called the spring constant. So the slope of the line is the spring constant. And basically what this means is that the larger that is K, the steeper that is this line will be. So if we pull open this little file here, basically you have a graph, if I can sketch it, that looks something like this. Weight stretch, amount stretch. This should be basically in newtons, this should be in meters. And you end up getting a line, like so, ultimately. And so your slope of your line is going to be the spring constant. Slope equals spring constant, and spring constant is sometimes represented by a K. And so the equation for this line basically says Ws is equal to Ks times X. Now there's more to it than this, of course. In fact, if you did a force that the spring itself is actually applying versus the stretch, you'd have to put a negative sign into this because of Newton's third law. But this is sufficient for us for now, and it should go through 0, 0, so it'd be plus 0. You could also put in total weight is Ks times X plus that amount of weight you had to hang to stretch it with. Either way, given that this question is asking us here that both have the same initial length, both have the same maximum length, and one weighs stuff that is 2 times as much. In other words, you can put 100 pounds on scale B, but only 50 on scale A. The implication here is that this stiffness factor right here must be larger for B than for A, because you basically have WS max is equal to, for A, is equal to 50 pounds. WS max for B is equal to 100 pounds. And X max for A and X max for B are the same. So basically you can write something like 50 pounds is equal to KSA times X max A. 100 pounds is equal to KSB times X max B. But that's also equal to KSB X max A, because B and A have the same maximum X. So looking at this, you have some number times this is 100, some other number times this is 50. Which one is bigger? Well, this one's got to be bigger because it gives you a bigger number when you multiply by the same thing. So that means that the larger spring constant must correspond to basically spring B. So we open this thing up and write in scale B's spring is stiffer. And again, recall that the spring constant is basically how stiff the scale is. So that means that because the spring constant is larger, then the stiffness is also larger, because the spring constant measures how stiff the spring is with all else being equal. So therefore we select scale B's spring is stiffer. Okay, so now we're told that suppose that you have this spring and you start adding weights and it does not stretch until you add 10 newtons, but then it stretches 10 centimeters for every 100 grams you add, and it wants to know what's the equilibrium weight W0 of this scale in newtons. So pulling up the directions again, they tell you quite clearly that W0 is the weight that you have to add before the spring begins to stretch. So this is sometimes called the equilibrium weight of the scale. It says that up here as well. Mark this weight as W0, the equilibrium weight in newtons. So I've been a little bit redundant here just to be sure that you catch what it is that I'm asking for in this quiz. So it says here that you don't stretch until you add 10 newtons. So that makes the equilibrium weight 10 newtons. So actually you just enter a 10 here, because you would read this line as if it said the equilibrium weight of the spring is blank newtons, and so I put in a 10. The next question starts off the same. Basically it says the spring does not stretch until you add 10 newtons, and then it stretches 10 centimeters for every 100 grams that you add. What is the spring constant for this scale in newtons per meter? Well, we've been told basically that you get 10 centimeters for each 100 grams. So this right here we need to convert into a weight, and that is basically the mass times the gravitational acceleration. So this is mass, this is free fall acceleration, which is actually just 9.80 meters per second squared. Alright, so basically this weight is saying that we have for every 100 grams, so we'll call that a delta W, we have 0.100 kilogram times 9.80 meters per second squared. So if you multiply these two things together, you get 0.98 newtons. This right here is basically like a delta X, and it is 0.10 meters. So the spring constant Ks is given by the slope of that graph of stretching weight versus amount of stretch. So the slope is delta W over delta X. So we would put 0.980 newtons divided by 0.10 meters, and so that is 9.8 newtons. Now, I probably should also work this for completeness the other way, which is to say that Ks, what happens if we don't do this conversion? Ks would be basically, instead of 100 grams, we'd have like we'd do like 100 gram times 9.80 meters per second squared divided by 10 centimeters. What would we get here? Well, you can see that there's a 10, there's a 100, so that leaves a 10 left over. So we'd end up with basically like 98, but we'd have these bizarre units: gram per meter per second squared per centimeter. This one right here was 9.8 newtons per meter. So let's go back to that question, and it tells us that the units we specifically want are newtons per meter. So we would have to convert this into newtons per meter, and we would do that by basically multiplying, because remember, 1 newton is the same thing as 1 kilogram meter per second squared. And then, so we'd basically need to convert this and this into kilograms and into meters. So we would have times 1 kilogram divided by 1,000 grams, and then that would in turn be, we got to get rid of the centimeters on bottom, so we have to put 100 centimeters per 1 meter here, and so you'd again get Ks is equal to 9.8 newtons per meter. Either way, we get the same answer, and so now we come here and we write 9.8 into this line, and that's why it asks on so many of these to a specific unit like this. It's telling you that you've got to convert your units if you haven't done that from the beginning. Next thing it asks, what kind of graph do you get when you plot weight versus spring length with spring length on the x-axis? You might interpret this to represent the total weight or the stretching weight. It doesn't actually matter which one you pick, because both of them are going to give the same answer. I'll show you what that is. Let's open back up my workspace here. I already showed you or told you that if we made the plot of the stretching weight plus x, we would end up getting a line like this, and that we could write Ws is equal to Ksx. I also wrote below it Wt is equal to Ksx plus W0. So what kind of graph would this make? Well, W0 is a constant, so this is constant, and it's also positive. So that basically means that you'd end up with a graph that looks something like this. Here is W0, this is Wt, here's x. So in both cases we have a line, and it is a line that is not horizontal. So we would put a non-horizontal line. Horizontal line basically would look something like this. Horizontal line just means your line is horizontal, like so. So it's not that kind of line, and it is it is a line nevertheless, so that leaves us with this answer. Question 8. Suppose the slope of a weight versus length graph for a spring gives 70 newtons per meter and the x-intercept is 0.30 meters. What is the spring constant for this spring in newtons per meter? Okay, so now we basically can open this guy back up again to remind ourselves when we look down here that the slope is the spring constant. Now this is slope of stretch versus weight, but weight versus length doesn't really change the slope. The total length just means you're adding to everything an additional x naught term. So that does not have any effect on the difference in x's, because if you add the same x naught to both points for your slope, in other words, if you have chosen to do total length versus stretch, then this thing right here would actually start off over here somewhere. So you'd end up with like a graph that's like this. Oops, I think I can draw it a little better than that. You'd have a graph that's like this. Notice that these two are parallel. So if I take the slope for this one and I take the slope for this one, I'm going to get the same amount of run and the same amount of rise for both. If I measure this and this, it's the same. If I measure this and this, it's the same. So that means that regardless of how you interpreted this question, the answer is the same. The slope is going to give you your spring constant. So the answer should be 70. Okay, next it says the same thing. It gives you an x-intercept, and then the spring begins to stretch immediately when you add weights to it. So how much does the spring stretch when you add 7.0 newtons to it? Notice that this is an x-intercept, so if I show this on the graph again, that actually corresponds to this point right here. This point right here is 0.30 meters, not newtons, meters. It stretches immediately when you add weights to it. So this actually is the line in question. And in fact, if I plotted the weight total versus x, it would actually look like this. Basically, W0 is 0 because it stretches immediately when you add weights to it. So this right here, by the way, is the unstretched length. And it's saying basically that W0 is 0 newtons because it stretches immediately. So as soon as you add weight. Okay, so now the question itself here is basically asking how much is it going to stretch when you add 7 newtons to it. So you can use the equation. The equation basically says this thing right here. So weight total equals 7.0 newtons. Weight 0 is equal to 0 newtons. Ks is equal to 70 newtons per meter. You did that on the last step. And want x. Alright, so x, according to this equation, is weight total minus weight 0 divided by Ks. And so that is 7.0 newtons minus 0 newtons divided by 70 newtons per meter. And so x, in this case, 7 divided by 70 is 0.1 meter. So it's going to stretch about 10 centimeters. And it basically just says how much does the string stretch by. So 0.1 meters. Now it asks the same question, except for it asks what is the length of this spring when 7 newtons are added to the end of it. Well, as I showed here, or as I stated earlier, the unstretched length is 0.3 meters. It's stretched by 0.1 meter, so the total length must be 0.3 plus 0.1. So that would be 0.4 meters. That one's maybe a little bit trickier because it's not hinted at so much in the instructions, but I do want you guys to think a little bit about what it is that you're doing in these. In the event that this was a total blindside, you at least should have 2 tries at it. Okay, next question. You have a spring whose total length you have measured against the force supplied. You obtain a line of best fit and find that this line contains the point 45 centimeters, 25 newtons, and 65 centimeters, 45 newtons. What is the spring constant of this spring in newtons per meter? Okay, so let's pull that up. Basically, what it just said is that you've been given these 2 points. So again, what these 2 points are, the first one, if we pull it up, is 45 centimeters, 25 newtons. So this point right here, 45 centimeters, 25 newtons. This point right here is the 65 centimeter, 45 newton point. So 65 centimeters, 45 newtons. All right, so again, the spring constant is given by the slope. So that is delta W over delta X. And so to get those deltas, we have 45 minus 25. That's the change in weight, 45 newtons minus 25 newtons, divided by 65 centimeters over 45 centimeters. So we have 65 centimeters minus 45 centimeters. And so Ks, therefore, 45 minus 25 is 20 newtons. 65 minus 45 is 20 centimeters. And so this is 1 newton per centimeter. Aha, but now let's look at what this question is actually asking us. Question is actually asking us here, what is the spring constant in newtons per meter? So that means that I need to convert my answer to newtons per meter. So let's open this guy up again. We have it in newtons per centimeter. So Ks is 1 newton per centimeter times 100 centimeters per 1 meter. So that gets rid of the centimeters, and that means that Ks is equal to 100 newtons per meter. So we open this thing up. Okay, so now let us turn to the last problem on this quiz. It basically starts off the same as question 11, and the question that it actually asks then is what's the unstretched length of the spring in meters. So we're told this, and then we're told this, and basically what we need to do here, well, I've written out again the spring constant and 2 points on the line. Essentially what's going on here is it's giving us a plot here of total weight versus length, and it's saying that this right here makes some sort of a line like this. So weight total is equal to basically like essentially question mark, but it's basically Ks times L minus L naught plus weight 0. That's the kind of equation that I'd fit to this line, where this point right here is actually L0. This difference L minus L naught is the stretch. So this length here is actually the total length of the spring. Okay, so the basic way that we can solve this equation is we come up here and we say, when is it that we obtain a length of L0 for the spring? And the answer is, well, when this weight is equal to 0. So when Wt is equal to 0, L is equal to 0. L is equal to L0 because x is equal to 0. So if x is equal to 0, x is equal to L minus L0, and that's equal to 0, then it follows that L is equal to L0. So now we can come up here and look at this look at these 2 points. Each point sort of implies an equation. The equations implied by these points, I'm going to number them, point 1 and point 2. So the equation for point number 1 is 25 newtons is equal to 100 newtons per meter times basically the length 0.45 meters minus length naught. And equation number 2 basically implies 45 newtons is equal to 100 newtons per meter times 0.65 meters minus L naught. And so the question is, solve for L naught. L naught occurs at 0 newtons is equal to 100 newton per meter times L minus L naught at 0. So one way of approaching this is to say, okay, I have for equation number 1, we'll just take that equation, I have 25 newtons that I've got to get rid of by decreasing the stretch on this spring. So how much is x for W equals 25 newtons? This quantity in here is actually x. So we have 25 newtons is equal to 100 newton per meter times x. So x must be 25 newtons divided by 100 newtons per meter. And so that is 0.25 meters. By the way, if we chose number 2, we would have had 45 newtons per meter is 100 times x. X is equal to 45 divided by 100 is equal to 0.45. Okay, well, notice that here we have 0.65 minus L naught is x. And here we have 0.45 minus L naught is x. So 0.45 meters minus L naught is equal to 0.25 meters. And this is using equation 1. If we used equation 2, we would have had 0.65 meters minus L naught is equal to 0.45 meters. Notice that both of these are going to give us the same equation, because if I wanted to solve this equation for what is the value of L naught, what I basically do is I say, okay, I need to add a plus L naught to both sides of the equation. And so what that gives me is 0.45 meters is equal to L naught plus 0.25 meters. This one right here says 0.65 meters is equal to L naught plus 0.45 meters. Okay, so now I subtract 0.25 meters from both sides of this one, or I can subtract 0.45 meters from both sides of this one. Again, I'm subtracting this much and I'm subtracting this much, and so I end up with L naught is 0.45 minus 0.25, which would be 0.20 meters. This one says L naught is 0.65 minus 0.45, which again is 0.20 meters. So either way I slice it, I've got 0.20 meters. So that means I basically need to put in 0.20 here. And so at this point, I should be able to save and submit. So now we see basically how we did. It says you did this right, did it right, did it right, did it right. You look down, all the answers are correct. We're done. Score 125 out of 100. So that's basically how you do this particular quiz. That's basically the solutions to every question on the quiz. So hopefully you found this video helpful, and thanks for watching.